Hey everybody, Mr. Viteri here again with another lecture, Unit 7, Day 5. Let's get right to it. So I wanted to continue on the Clean Air Act. There are about 10 acts of legislation that we need to go over, and I want to do a project on that after we're done with our Unit 8 and Unit 9. We've kind of covered some of them, CITES, CERCLA, Clean Air Act, Clean Water Act, but we want those fresh in our memory. So let's look at the Clean Air Act. The Clean Air Act was established in 1970. 1970 is a magical year. EPA was established as well. And with the Clean Air Act, they have established what they call criteria air pollutants. And these are going to be identify certain pollutants that are in our air that we could measure that are going to dictate how we manufacture our machines to set limits on the emissions. So, for instance, your car cannot produce such amount of SO2 or CO or lead. It has to be below a certain parameter. So basically, they're setting the limit. Okay, and those criteria pollutants are carbon monoxide, lead, ground level ozone, particulate matter, nitrogen dioxide, and sulfur dioxide. Okay, so try to get those, put them on an index card: carbon monoxide, lead, ground level ozone, particulate matter, nitrogen dioxide, and sulfur dioxide. I've seen also on the EPA's website, they call it nitrogen oxides, sulfur oxides, carbon oxides, particulate matter, lead, and ozone. Okay. Try to get those in your mind. Other parts of the Clean Air Act would be removal of lead from unleaded gasoline, from gasoline rather, now that it's unleaded. And another thing, and some people get upset with this, me particularly, I understand the frustration, and I'll give you an example. But if you have a gas container, if you mow your lawn and you use gasoline and you fill it up, the red container that you have has to have an air trapping system, meaning that you can't just have the nozzle and the gasoline in there because it goes into vapor form very easily. Escape. There has to be some air trapping mechanism. So there's a special nozzle on there that I know on my gas tank, I have to press the nozzle while I'm filling the gas tank. And if I don't press this nozzle, then that means none of the gas will come out. Okay. Why I say I'm a little upset because I bought a brand new snow blower a couple of years ago, so it's relatively new technology, and it wasn't idling properly. If you don't know what the word idle means like when you turn on a car and it just is starting and the engine is on. So when you turn on this snow blower, it would just kind of have a rough idle, and it seemed like it wanted to die, like it wasn't getting enough fuel. Anyway, I got online. I'm like, brand new, you know, snow blower not working properly, and they basically said that there is a nozzle on the air intake that doesn't allow enough air to go in because it wants it to idle basically they don't want you to idle that thing, so it's designed to actually shut off. If you're going to use it, you should be using it and revving the engine. Does that make sense? Because idling is basically you have this thing and it's basically wasting fuel. I understand if you're in a car or you're in a truck, sometimes they don't want to deal with starting the car up again, so they leave it idling. But this would be part of the Clean Air Act, designing something that is going to make it more difficult to do something like idling. Idling is dangerous. Idling creates fumes, and you're not even going anywhere. Turn off the car, darn it, and let's continue. So those are some particular things that are involved in the Clean Air Act. So if we look at this image over here on the right, we could see from 1970 to 2017 that there has been a decline in these air pollutants, all due to the Clean Air Act. And it's always fluctuating. So it's not like, once we've designed something, then we don't have to redesign it. So every year it has to get updated. So we try to tweak it a little bit every year. So every year, 5%, 5%, 5%. And we're coming to that point. And I think a goal is to be at zero emissions or carbon neutral. And so that's what we're trying to gear the technology towards. It's a pretty cool way of having innovation and creating jobs and creation and adjusting and tweaking machinery. And that's why a brand new car is different from, let's say, a car that was made in the 70s. The emissions are going to be different, so therefore the design of the engine has to be different. And so sometimes it's little tweaks that make them more efficient in their design. All right. So yes, it has been successful. We could be even more successful in the Clean Air Act by trying to reach carbon neutrality, which basically means that the amount of carbon is being produced is going to be equal to the amount of carbon being sequestered. All right. There are different technologies that can be employed that way. Perhaps even, if you are going to burn fossil fuels, can you return some of the trees? Are you planting trees? Are you sequestering the carbon? Are you putting it into the ground? Are you using clean coal technology? Are you using wet scrubbers? Are you reducing what you are creating? So let's continue. So yesterday's lecture we left off on this slide, and we were talking about the problems with acid deposition and how it can hurt waterways as well as foliage or trees. Um, Expert level understand that as this acid deposition goes into the ground, it makes aluminum very mobile, and it gets uptaken by the plants, and that weakens the plants. Okay, it's toxic to plants. It also strips the plants of calcium and magnesium. So now they're not getting calcium and magnesium, a vital nutrient that they need. Okay. Not only does acid deposition do that, but aluminum also goes in the runoff. And now, if that goes into a body of water, like a lake, it could concentrate, and aluminum is toxic to fish as well. It could build up into their gills and prevent them from breathing. So, right there, acid deposition is so devastating to certain places. Understand it, it's definitely on the CED. Now, here's a common misconception, and I want you to understand ocean acidification in comparison to acid deposition. All right. Now, the ocean is a lot larger than any lake, okay, anywhere. All right. The ocean is like almost infinite in comparison to what a lake is going to be. A lake, since it's such smaller, can become more acidic as acid deposition happens. Don't get confused with ocean acidification being caused by acid deposition. The ocean is not really getting more acidic because of acid rain. I mean, it could be affected, but it's just so big, it's not really being affected that way. That doesn't mean that the ocean is not getting more acidic. It just means that there's a different reason that the ocean is getting more acidic. Now, the ocean is getting more acidic. We have some data regarding that. And I think we're going to have a graph in one of our next slides to actually show you that. But why is it becoming more acidic? Well, it's getting more acidic because there's more CO2 in the atmosphere. CO2 plus H2O vapor is going to make carbonic acid. Okay? So you could think of, as the CO2 emissions are going up, and we know that CO2 emissions are going up in our atmosphere, therefore, that CO2 is also going to increase in the amount that's in the ocean. Then the CO2 mixes with the H2O, making carbonic acid. So if there's more carbonic acid in the ocean, therefore the ocean becomes more acidic. Okay, and that's a problem. That's a problem because shellfish, or organisms that have shells, their shells will dissolve in acidic conditions. Okay, the ocean right now is slightly basic. If it becomes more and more acidic, these shells cannot form. So therefore, these shellfish don't have their protection. So therefore, they're going to be easily preyed upon predators. So they're going to lose their defense. Okay, and that's a huge thing because shellfish could make up the base of a food chain. So you can cause a trophic cascade and destroy all the organisms that are in the ocean. All right. So understand that ocean acidification gets caused by an increase in CO2. And so let's look at this image here. We have seawater and we have a pH. It looks like it's above 8. And now it's becoming more acidic. Doesn't mean that the ocean is acidic, it's just becoming more acidic. There is going to be a threshold where these shellfish organisms can no longer sustain and make their shells, and therefore they'll start to die. Okay, so how can we reduce this? Well, we're trying to bring CO2 emissions lower in the atmosphere, and therefore this would reverse. Okay, there wouldn't be that much acid in the water, and therefore it could possibly increase the pH, and the aquatic organisms or the shellfish could have shells. Now, I gave you a lot of information. I want to give you a little tidbit. If you were going to explain that on a free response question, you want to be long-winded and explain the whole process. I remember grading this question. There was a question on ocean acidification maybe 3 years ago, 2 years ago, 2 years, 2 or 3 years ago. And you had to explain that the shells would dissolve, and since their shells would dissolve, you had to use that word dissolve. If you didn't use that word dissolve, if you wrote break, if you wrote they wouldn't have shells, that didn't count. You had to use the word dissolve, because that's the chemical reaction that's occurring. The acidic conditions are not allowing the shells to form because they're being dissolved, and therefore, if the shellfish don't have the shells, they are going to be predated on, and therefore they will decrease in their numbers. All right. So you had to say that because the shells are necessary for health and their safety, their security. All right. Okay. Let's continue. So here is an image of some shells that are being dissolved by acidic conditions. Now, coral reefs could also dissolve because of ocean acidification. Now, there's a common misconception, once again, that I don't want you to think that coral bleaching is the same thing as ocean acidification. It is not the same thing. These are two different things. All right, we'll talk about coral bleaching another unit, I believe. But right now, we're talking about ocean acidification in highlights of acid deposition. Acid deposition doesn't cause ocean acidification. Rises in CO2 emissions in the atmosphere cause this. All right. So look at these shells; they're not forming, and this coral reef looks like it's dissolving because the ocean is becoming more acidic. Now here is a great image. Let's try to understand what's going on. It's a complex image, and so let's take our time with it. All right. First off, let's identify all the three different lines. One of those lines is this orange line, and that's going to be atmospheric CO2. Okay, that means atmospheric CO2. Now, this one is seawater CO2. And so if we see this correlation here, we have atmospheric CO2 going up, and then we have seawater CO2 also going up. Okay. Now, how do we know we're going to use this this axis versus this axis? Well, it says CO2 in here, so we're going to use this. So this means that the emissions here are roughly about 400, right? 400 parts per million CO2 emissions, and there's a direct correlation between aquatic CO2. So that's easy to assume. If atmospheric CO2 goes up, then aquatic CO2 is going up as well. Now, as CO2 goes up, what's happening to this blue line? So let's identify what's this blue line. So blue line is seawater pH. And now, I'm not going to use this scale. I'm going to use this scale on the right because it's pH. Notice that it is coming down. So there's a correlation between if this goes up, this goes down. And as this continues to go up, this will continue to go down. Also make special note that the pH is still not acidic at this point, but it's becoming more acidic. Okay? It's going to get to that threshold where those shells cannot form. All right, so there needs to be a change that must occur. All right, let's continue. All right, so like I said before, corals dissolving is caused by ocean acidification. But coral bleaching is different. Coral bleaching is going to be caused by an increase in temperature of the corals themselves. Okay, The corals are beautiful. It's a complex relationship between symbiotic algae and the coral polyps themselves. If you don't know what corals are, they're like these sessile organisms. I hate using big words. These organisms that do not move. They're basically filter feeders. They're like little clams, and they have there's also these algae, photosynthetic algae, that live on them. All right, and they create the beautiful colors that they have. All right. Now, if it gets too hot, the algae die, and that mutualistic relationship also ceases to exist. So therefore, the corals start to die. Instead of being beautiful colors and full of life and photosynthesis going on, they become white and bleached. I don't know if you've ever seen a piece of coral. I think it's illegal at this point due to CITES. Um, but they're always white. How did they turn white? Well, they're bleached. They're bleached, so if they had any organisms on them, they would stink up your house. So you typically leave them in the sun, everything dies, and that's bleaching. Or you could put them in bleach, and that's going to kill them as well. So understand that coral bleaching is being caused by global warming. And as the oceans become warmer, and get this, the symbiotic algae that live with the corals die. Ooh, you sound so smart. Just say it. Just say symbiotic algae. Oh my God. And try to understand what that means. You're just going to be a genius. And if you know the difference between ocean acidification and coral bleaching, you're a genius. You own the room. Okay? You own the room. All right? And you could really think about this because corals are really, really important. They have the most primary productivity than any other biome. Okay, so that means there's full of biodiversity in there. Australia has the biggest coral reef. It's in Australia. It's under attack. You can watch a YouTube video on here to learn more about the Australian Great Barrier Reef. You're not supposed to touch the corals. If you ever go to a place in a vacation, do not go on vacation. Do not leave the United States. You heard my story. But anyhow, you're not supposed to touch the corals. You could rip pieces off. All right. Um, Corals are under attack. There's so many different things that are attacking corals, but let's name a few. Okay. Corals can die because people dynamite fish. They just throw a piece of dynamite, corals break into little pieces. All right, not a good thing. Okay, people are also going to, love what it looks like, and they want to take a piece home. All right, do not do that. All right, the corals need to be there. They grow on top of each other. You take a piece, the coral has to regrow. It doesn't grow that fast. Right? It's not going to like grow like kudzu or anything like that. And why do we need these things? Well, they preserve biodiversity. They reduce beach erosion. Okay, this was a thing in Long Island, specifically Mastic Beach. I would go to Mastic Beach, Shirley. This might make sense, might not make sense. Even Sandy Hook. Imagine, like, as soon as you get to the parking lot, and this might even be a better thing. I know if you go to Sandy Hook, you go to the parking lot, you have to kind of walk a long ways to get to the water. Imagine that water was just really close, though. And that means it's beating on Sandy Hook. It means Sandy Hook could go underneath. All those houses or the bathrooms where Sandy Hook is basically going to get underneath the water. Well, if you had a wave barrier, if you had something that's protecting the waves, this will reduce beach erosion. In Mastic Shirley, the beaches had to be refilled because there was just too much erosion going on. The coral reef in the Long Island Sound, right? It provides food for organisms because a lot of fish eat there, and we could fish those organisms. It provides shellfish. They're nurseries for school. There was a great documentary film. You know what it's called. He lost his, he got lost. I don't know what's his name. I don't want to say his name because it's going to be on YouTube. And also carbon sequestration. So a lot of photosynthesis goes on. A lot of primary productivity goes on there. So they basically absorb all of that. All right. Okay, I believe that's going to complete our lecture for today. We'll finish up on Monday, and I want you to enjoy your weekend. Talk to you later. Bye.